The Z1 electrical system can be divided into the charging, ignition, starting, and lighting groups. All except the lighting circuits vary to an extent from other motorcycles, and these differences will be explained in this tape. We'll begin with the charging circuits, examining the parts and checking them in the same order that you would to find a charging problem. This is a wiring diagram of the Z1 charging circuit. It contains a dynamo, rectifier, battery, and regulator. The AC produced by the dynamo is changed to DC by the rectifier and is used to charge the battery. When engine RPM rises, the dynamo voltage also rises, so the regulator is used to keep the voltage down and stop it from overcharging the battery and burning out the lights. The dynamo can be disassembled into the rotor and stator. The rotor is made up of permanent magnets and so needs no brushes or slip rings. The stator contains coils wound on laminated iron cores. They are wired together into 3 sets so that 3-phase AC can be generated. Although there is also a delta method of connecting the 3 coil sets, a Y connection is used in the Z1 armature for maximum voltage output. The voltage from each phase or set of coils overlaps the next as shown so a smooth voltage output can be obtained. Before trying to check the dynamo, first make sure the battery is good. Check the voltage at the battery terminals. Normal voltage is 12½ volts or more. If the battery voltage is less than 12 volts, charge the battery before any further tests are made. When charging the battery, follow the manufacturer's instructions. If the electrolyte level drops during charging, add only distilled water, as ordinary tap water or additional acid would ruin the battery. Clean the battery terminals thoroughly before installing the battery, and after installation, coat the terminals lightly with grease and check that the vent hose is not folded or pinched. Take off the right side cover, pull the green plug to disconnect the regulator, and make sure all the lights and turn signals are off. Switch the meter to the 12 ampere range and insert the meter leads into the correct holes for measuring this current. Disconnect the positive battery lead and connect the positive meter lead to the battery wire that was just disconnected, and connect the negative meter lead to the positive battery terminal. Now kick-start the engine. Do not use the electric starter, as this would damage the meter. Set the engine speed to 4,000 RPM and read the charging current from the ammeter. It should be 9.5 amperes or more. Turn off the engine, disconnect the meter, and connect the battery wire back onto the battery. Change the meter leads to measure DC voltage, set the meter to the 30-volt DC range, and connect the meter leads across the battery, meter minus to battery minus, and meter plus to battery plus. Start the engine, set it to 4,000 RPM, and note the meter reading. Normal voltage is between 15 and 20 volts. If charging voltage or current is below normal, next remove the blue plug and check the dynamo. Set the meter to the R times 1 range and zero it. Sticking the meter leads into the back of the blue plug that was taken out, measure the resistance between first the white and pink wires, second the white and yellow wires, and third the pink and yellow wires. All 3 readings should be about 1/2 ohm. If there is less or zero resistance, the coils are shorted. if the ohm meter needle does not move at all or gives a high reading, a wire in the coils or in the cable is probably broken. Using the meter on the highest resistance scale, also check that none of the 3 wires is shorted to ground. If there is any reading at all, there is a short in the dynamo or wiring cable. If the dynamo checks good, the charging problem may lie with the rectifier. The rectifier contains 6 diodes connected in a bridge circuit to perform full wave rectification of the dynamo voltage. That is, it changes the AC into smooth DC. This is a wiring diagram showing the diodes in the rectifier. The diodes are semiconductors, meaning that current will flow through them in only one direction. Except for a small amount of leakage current, no current will flow in the other direction. So the rectifier can be easily tested with an ohm meter, seeing that the rectifier has low resistance in one direction and high resistance in the other. If a diode overheats or if too much current flows through it, it will short and conduct in either direction. Unplug the white rectifier plug and disconnect the white wire. Set the meter for resistance measurement using the R times 10 or R times 100 scale and measure the resistance between the white wire and each of the other wires. Then reverse the meter leads and measure the resistance in the opposite direction. Resistance should be low in one direction and be more than 10 times as much in the opposite direction. Now do the same thing again between the black wire and each of the other wires. Again, resistance should be low in one direction and more than 10 times as much in the other. If the dynamo and rectifier tested good, the next part to check is the regulator. But since the Z1 has an electronic regulator, first let's see just how the regulator works. To understand the operation of the electronic voltage regulator in the Z1, you must first know a little about 2 of its most important components, the thyristor and the Zener diode. In an ordinary diode, current will flow from the negative side to the positive side and will not flow in the opposite direction. But if too much voltage is applied in the reverse direction, the diode will break down and conduct in either direction, making it worthless for use as a rectifier. The Zener diode is like an ordinary diode except for 2 points. We can manufacture the Zener diode to break down at the exact reverse voltage that we want it to, and we don't have to throw it away once it breaks down, because it will return to normal as soon as the voltage is lowered or taken away. This makes it very useful in voltage regulators, as it will break down and tell us when the voltage is too high. The thyristor is also like an ordinary diode in that it will not conduct in the reverse direction. But the thyristor needs a momentary signal at the gate lead to tell it when to start conducting. And every time the voltage across it is taken away or reversed, it stops conducting and waits for another signal before it will conduct again. This simplified diagram of the Z1 regulation circuit shows how the regulator works to control one phase of the 3-phase voltage. We'll use the Zener diode to signal the thyristor when the voltage is too high, and when signaled, the thyristor will conduct and return the excess voltage to the dynamo. When the dynamo coil at the left is positive at point A and negative at point B, current will flow from the coil at B through D2, up through the battery to charge it, and then back through D1 to the dynamo. But now suppose this voltage starts getting too high. The Zener diode connected to the top of the battery senses this and breaks down. A little current from D2 goes up through the negative thyristor lead and out through the signal lead to give the thyristor a push to start conducting. and the thyristor acts like a short circuit across the dynamo. Instead of the current going to overcharge the battery, it comes out of D2 and goes through the thyristor right back to the dynamo. Of course, since this is an AC dynamo, pretty soon the coil voltage will reverse, and all current flow in the thyristor will stop and wait for another signal from the Zener diode. Because this is a three-phase dynamo, all the regulator and rectifier parts you just saw are multiplied by 3, and with a few extra parts to hold them together, form the Z1 charging circuits. Looking now at some of these extra parts, we'll find 2 more thyristors and resistors added underneath the first and second thyristors. The first resistor takes some of the voltage from thyristor 1 and uses it to signal thyristor 2, so it will start conducting to control the second phase of voltage. Then the resistor under thyristor 2 does the same thing to signal thyristor 3, which handles the third phase. All these diagrams and explanations can be found in the Z1 shop manual. So now we'll go on to regulator testing. First, reconnect all the wires disconnected during previous testing. Start the engine and set it at 4,000 RPM using the throttle friction adjusting screw to hold it there. Set the meter to the 30 volts DC scale and connect its leads across the battery. Meter minus to battery minus, meter plus to battery plus. If the voltage across the battery is not between 15 and 16 volts, the regulator may be defective. Remove the regulator from the motorcycle for testing using the offset socket wrench. Set the ohm meter to the R times 10 scale and measure resistance between each of the 5 wires and any other wire. There should be no reading between any of the wires in either direction except between the black and brown wires, which should have about 1,000 ohms resistance in either direction. Next, connect 14 volts DC between the black and brown wires, minus to black and plus to brown. Then measure resistance between the black wire and the blue, pink, and yellow wires one at a time. Reverse the meter leads and take the same measurements again in the opposite direction. There should be no reading no matter in which direction the ohm meter leads are connected. Be careful the test leads don't touch the black and brown wires at the same time, as this will put the meter across the battery and will burn out the meter. Now raise the voltage to 17 volts. Do not apply over 18 volts even momentarily, as the regulator will be damaged like this demonstration one was. Again, connect one ohm meter lead to the black wire and touch the other lead to the blue, pink, and yellow wires one at a time. Then reverse the leads and measure the 3 resistances again in the opposite direction. In one direction, there should be a low resistance reading for all 3 wires, and there should be no reading at all in the opposite direction. Note that this regulator cannot be disassembled. The 3 small screws in the face of the regulator are for heat dissipation only. If they are loosened or removed, the regulator will overheat and short. Next, we'll work with the ignition system, which is shown in this diagram. The ignition system is divided into 2 complete circuits, one to fire spark plugs 1 and 4, and the other to fire spark plugs 2 and 3. Current from the battery goes through the contact breaker points, whichever set happens to be closed at the time, and flows through the primary winding of the ignition coil. When the contacts open, the sudden interruption of current flow through the primary, along with the high turns ratio of the windings, causes a high voltage to be produced in the coil secondary, and a spark jumps across the 2 spark plug gaps. Combustion does not take place in both cylinders at the same time, however, because this is a 4-stroke engine, and although 2 pistons at a time rise together, one is always on its exhaust stroke while the other is on its compression stroke. This means that while one of the two cylinders will contain compressed gasoline mixture to burn, the other will contain only exhaust gases that will not burn. If the breaker point surfaces become dirty, burnt, or pitted, or if the spring forcing the points together becomes weak, misfiring and poor engine performance will result. Oil on the point surfaces will cause burning, and so must be cleaned off with trichloroethylene or some other oil-free solvent. For minor point damage, the point surfaces can be dressed with emery cloth or oil stone. But if the points are badly pitted or burnt, they should be replaced. A close-up of the contact breaker circuit shows a condenser connected across each set of points. This condenser serves to absorb most of the spark that tries to jump across the contacts every time they open. This not only keeps the points from burning or pitting, but also helps produce a stronger spark. After long use, the condenser may weaken or short. A shorted condenser will cause a very weak ignition spark, or perhaps no spark at all to two plugs. A weak condenser will allow sparking at the contact breaker points. When that happens, the ignition spark at the plugs will be weak, and the breaker points will burn and pit quickly. It is best to check suspect condensers with a condenser checker, such as the Kawasaki Electrotester. But in any case, the condensers are inexpensive, and by replacing them whenever the breaker points are changed, or whenever there is reasonable doubt that they are good, more time-consuming and expensive trouble can be avoided. A defective ignition coil may also cause ignition trouble. Since one coil in the Z1 produces a spark voltage for spark plugs 1 and 4, and the other coil for plugs 2 and 3, an open wire or short in one coil will cause a weak spark or no spark in two cylinders. Remember that each pair of spark plugs are connected in series, and if either plug is bad or if one wire is not properly connected, the spark to both plugs will be lost. With this in mind, check out the spark plugs before bothering to look at the coils. The most reliable test of coil performance is made with a 3-point tester. Connect one high-voltage coil lead to each high-voltage lead of the tester. A ground is not necessary. Connect the other two tester leads to the coil primary wires. If the coil will not produce at least a 7mm spark using such a tester, the coil is defective. The ignition timing in the Z1 is directly controlled by the cam on the end of the crankshaft, which pushes the contact breakers open at the correct moment. But this cam in turn is controlled by the automatic timing advancer. The heart of the timing advancer is an assembly of weights and springs connected to the timing cam. As the speed of engine rotation increases, the weights are thrown farther and farther outward like those on an engine speed governor, and the weights pull on the point cam in the direction of rotation, which advances the ignition timing. The speeds at which the advance start and end are controlled by the spring tension that resists the weight movement outward. This graph shows that up to 1,500 RPM, timing is 5 degrees before top dead center. But between 1,500 and 3,000 RPM, timing advances until it reaches the maximum advance of 40 degrees before top dead center. When checking for correct timing advancement, note that there should be grease inside the cam between the timing cam and the advancer body. If this grease becomes hard or used up, the cam will not turn and timing will not advance or could stick in the advanced position. And now to wind up discussion of the ignition system, we'll briefly cover the simple job of setting ignition timing. First, turn the crankshaft so that one set of contact breaker points is open to its widest point. Check to see that the gap is between 12 and 16 thousandths of an inch. If it is not, loosen the two breaker assembly mounting screws, pry the points to the correct gap, and tighten the screws back down. Follow this same procedure to adjust the gap for the other set of points. Now turn the crankshaft until the timing mark coincides with the 1 in 4 F mark on the timing advancer. Set the ohm meter to the R times 1 scale and connect one lead to the engine or chassis ground and the other lead to the wire or spring going to the points for plugs 1 and 4. Loosen the adjustment plate mounting screws and pry the plate around to find the point where the ohm meter needle flickers. This is the point where the points are just starting to open and timing is set there. When this point is found, tighten the screws back down. Next, use the F mark for cylinders 2 and 3 and follow these steps one more time. If for some reason either adjustment plate will not turn far enough to permit correct timing adjustment, the entire mounting plate can be moved slightly to provide adjustment slack. For an actual check of timing adjustment and of advancer operation, connect up a strobe light and run the engine. At 1000 RPM, the timing mark and F mark should coincide. At about 3000 RPM, the pin of the timing advancer should coincide with the timing mark. If timing is off, retrace the adjustment procedure and also check that the advancer assembly is not damaged or sticking. Next, we'll take the electric starter. The Z1 starter circuit is shown in this wiring diagram. It includes the battery, starter, starter relay, and starter button. To prevent damage to the starter button from the comparatively heavy starter current, only a small current to operate the starter relay is designed to flow through the button when it is pushed. Then when the relay operates, its heavy contacts provide a path for current to turn the starter. The starter itself consists of a yoke, armature, brushes, and their associated parts. The yoke contains 4 poles with the field coils wound on iron cores. The armature contains coils terminating in a commutator, and carbon brushes riding on the armature provide connections between the field and armature coils. If the carbon brushes do not make good contact, the result is the same as if the coils themselves were defective. The starter will not turn over. When the carbon brushes wear down short, the spring holding them onto the commutator lengthens and exerts a weaker force, bringing about possible brush contact failure. Normal brush length is about 1/2 inch. Any brush worn down to 1/4 inch or less should be replaced. If the commutator becomes dirty or scratched, clean and smooth it with fine sandpaper, being careful to clean off any sandpaper particles afterwards. Dust from the carbon brushes that collects between the commutator segments partially shorts out the coils and should be scraped out. Check for continuity between each two commutator segments using the ohm meter on the R times 1 scale. No reading between any two indicates a defective armature. Using the highest ohm meter scale, check that there is no continuity, that is, no reading, between the armature shaft and any of the commutator segments. Any reading indicates a shorted armature coil. Again, using the R times 1 scale, check that there is continuity between the insulated carbon brush and the starter cable. No reading indicates an open in the field coils. Using the highest ohm meter scale, check that there is no continuity between the insulated carbon brush and the yoke. Now going to the starter relay, here is a diagram of the relay showing its construction, although the relay cannot actually be taken apart. When the starter button is pushed, current flows through the starter relay coil, setting up a magnetic field. This moves the armature down to close the contacts and provide a path for starter current flow. When the starter button is released, a spring returns the armature to its original position, the contacts open, and starter current stops. To check the starter relay, disconnect the starter cable from the relay and connect an ohm meter across the relay from the starter wire terminal to the battery terminal. Set the meter to the R times 1 scale, and when the starter button is pushed, the relay should click and the ohm meter should read 0 ohms. If the relay clicks but the ohm meter does not read 0, the relay is bad. If the relay does not click, check the battery, starter button, and wiring before deciding the relay is defective. This concludes our guide to Z1 circuitry. For more detailed information, please refer to the Z1 shop manual.